Okay, here's the last part of the notes for Unit 5. Our goal will be to use the multiplication rule in conjunction with what we know about permutations and combinations to solve counting problems and also build probabilities with that. And then 5.6 right here just brings it all together. First off, you need to do this warm up, and you should do it on your own, so pause the video to make sure you understand. All right, here's the story. Wile E. Coyote is pursuing the Roadrunner across Great Britain towards Scotland. The Roadrunner chooses his route randomly, such that there's a probability of 0.7 that he'll take the high road and 0.3 that he will take the low road. If he takes the high road, the probability that Wile E. catches the Roadrunner is 0.01. If he takes the low road, the probability that the Roadrunner gets caught is 0.05, or 5%. So first thing you want to do is make a tree diagram. I know last semester we could make a table too, but please make a tree diagram. That is what they want for this class. And you can see that we have the high road versus the low road. That's the first thing that can happen. And then we have caught or caught complement, which would be not getting caught. So your tree diagram should look like that. Okay, what is the probability that the Roadrunner gets caught? Okay, so there are two ways that he could get caught. He could get caught using the high road, so 70% chance that he takes the high road times 0.01 that the Roadrunner gets caught, 0.7 times 0.01 because it's high road and caught. And remember when you're saying and, that is multiply, or, which means plus, he could take the low road and get caught. So that is where I got that 0.022 or 2.2%. And that overall is the probability of being caught. Now we're going to put it together with a conditional probability, or probability that took the high road, given that he got caught. So we're going to use our conditional probability formula, which is right here, the probability of high road given caught. You would never want to do caught given high road because we already know that answer. Caught given high road would be 0.01. So that formula is the same as the probability of high road and caught all over the probability of caught. Okay, so you can just put the numbers in. This right here is my denominator. Okay, and I simplify, so 0.318. There's a 31.8% chance that he took the high road if we know he got caught. I wanted to go on the side a little bit and just talk about how you could have done this without using the formula. If you are ever given a picture or a table, you do not need to use the formula. So here's a story problem. I have 10 people who own a garage, and I have 14 people, these numbers really shouldn't go out here, but I'm trying to make it clear, that have a pool, and I have 4 that have both. So that would be garage and pool. Okay, so the probability of garage then is 7 out of 20 because we have 10 that have a garage, or we could actually look at it this way, 3 that just have a garage, 4 that have both, 10 that just have a pool, plus 3 that have neither, so that's 20 total, and 7 of those in the red circle have a garage. So the probability of pool would be 14 out of 20, and garage and pool then would be that 4 out of 20. If I wanted to find the probability of garage or pool, this means or, okay, this is the addition rule that your notes talked about or your book talked about, where you do the probability of having a garage, so that's everybody in the red circle, plus the probability of having a pool, okay, so that's everybody in the blue circle, but notice I overcounted the middle, so you have to subtract the overlap, or 17 out of 20. And again, if I had this picture, I wouldn't bother to use this formula. I would have just said 3 plus 4 plus 10 and gotten my 17. So that's the addition rule. Now let's go back to the conditional that we just did with the Roadrunner. If you look at that, what is the probability that they have a garage given we know they have a pool? So that is garage and pool over pool. Well, garage and pool we already said was 4 out of 20, so that's where that came from. And the chance that they have a pool all by themselves, excuse me, I did that wrong. Garage and pool is 4 out of 20. And the chance that they have a pool total is 14 out of 20. And we know when we divide fractions, we just multiply the reciprocal, what gets rid of the 20, and that is 4 out of 14. But again, if I had this picture, I would not use this formula. I would have just said, how many people total have a pool? Well, that is 14. Of just those 14 people, how many also have a garage? That is 4. So the formula is very useful for a story problem like this, but if you are given a picture or a tree, it is not necessary. All right, on to the new stuff, the multiplication rule. Okay, let's suppose you're preparing for a wedding and you need to pick out tuxedos for the groomsmen. Men's Tuxedo Warehouse has a Build a Tux feature which will allow you to look at certain combinations and build your tuxedo online. Let's suppose you have the components narrowed down to 2 jackets, 2 vests, and tie combinations, and 3 shirt colors. How many total combinations might there be? Well, here's a tree diagram. So you can see right now that you've got 2 jacket combinations, which would be 2 right here, and then you need to pick a vest, okay, and a tie, so that's 2 other combinations right here. And then once you pick that, you have 3 options for your shirts, so that's 3 right here. So this was jacket, vest, and tie, and shirt. And what they call it the multiplication rule, because if you're saying something and something else and something else, you would multiply. You can notice that on this tree, this is a picture of all the combinations, and so this would be one option. This would be another option, and if you counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, but using the multiplication rule is much easier. Let's do a couple more examples. Okay, so this is what your book says. It says if you're doing something like that, you just multiply all the options. Here's the deal with repetition. How many 7-character license plates are possible if the first 3 characters must be letters and the last 4 must be digits? And repeated characters are allowed, which we know is the case. So what you do is you think about it space by space. Okay, the first letter or the first spot on your license plate could be one of 26 letters. The next spot could be one of another 26 letters, and the next 26. Now they want numbers for the last 4. Well, 0 to 9, that's 9 plus 0, that's 10 options for the first spot, times 10 times 10 times 10, or this many different license plates. If instead they didn't let you repeat, then the first one would be 26, but the next one would be 25 because you couldn't use the number or the letter that you used here. And so here's an example of that over here. Many garage doors have remote access keypads outside the door. Let's suppose a thief approaches a particular garage and notices that 4 particular numbers are well used. If we assume the code uses all 4 numbers exactly once, how many 4-digit codes does the thief have to try? So you kind of look at it and you realize that maybe the numbers 1, 5, 7, and 9 are worn down, so they know it's some combination of those. Okay, so the thief will say, well, the first number could be any one of those. Okay, so there were 4 options. Well, maybe the first number was a 1. So now there are 3 separate options for the next number. Maybe they picked 9, so that one's gone. Okay, so this is 9. So now there are 2 options for the next number. And now they pick 7. So there's only 1 option for the last number. And if you multiply those together, 4 times 3 times 2 times 1 is 24. Although we all know that if this was really a garage code, you could have repeat. So instead it would be 4 times 4 times 4 times 4 instead. All right, so that is the multiplication rule. Now we need to talk about permutations and combinations, which you should have learned in secondary 3. Okay, and I'm going to skip all of this. Okay, the first thing we have is right here.